Hello, my name is Raquel Herrera, and today I'm going to be doing one of the problems for Math 2000, which is our video assignment. The problem is to find the volume of a donut, or the official term for it is a torus. So I'm going to be showing you. I already have my work done, but I will go through the steps. So here are the steps. Okay. So first I'm going to do this by revolving a disc. And this will be the disc that I'll be revolving. So you're going to see that I'm going to revolve this around the y-axis. And it's going to go around like this. So that's how you're going to imagine the image of that donut. Because basically it's a circle going around. That's how it's going to be like. My coordinates is capital R, comma 0. And this is going to be R. As you can see, this is the y-axis and this is the x-axis. Now, as you can see also here, these are going to be the bounds. This is going to be the lower and the upper bounds. So this is going to be negative r, just a variable, and positive r. So those will be the upper and lower bounds. I have the equation here for the circle, for the disk. It's going to be x minus r squared plus y squared equals r squared. And I'm sorry that I did use capitalized r and lowercase r, but if you just look through the steps, then you'll see which r I'm talking about. So I just try to solve for x. And the reason why I do that is because we're revolving this around the y-axis. So when we do this, we're going to have r plus and r minus the square root of r squared minus y squared. So I have the equation here with the plus and the equation here with the minus. Now, the equation for the integral to find the volume, you need to find the integral of the area. So that's why I have volume is equal to pi r squared dr. This is important to know because pi r squared is equal to the area. If you take the integral of the area, you're going to find the volume. So the next step that I have in here is to plug this into here. And in this case, I'm sorry that I used the same one, but this should be like dx squared. That's what I'm plugging into. So we have v is equal to pi, and pi is just a constant, so you're allowed to take it out of the integral. Now, I don't have bounds here, but I'll tell you which bounds they are later. Actually, I should have them already on here, but I put them here. So, but you have the positive squared minus the negative squared. And that's because we're trying to get both of the whole disk. So you just plug in, they're both squared because that's what it says in here in the area. And this is on dy. And dy because we're rotating around the y-axis. Now when we plug this in, this is a long process, but it's just basic math. You just simplify it. So I didn't show that on here, but I just want to make sure that that's what I did, and you get 4r square root of r squared minus y squared d theta. That's what you get. If you want to go through the steps, you can, but to make sure that I got it right, but I'm pretty sure. And this is what you get. And so we have, again, dy. And then now I put the bounds, and I'm going to show you what the bounds are. It's negative r to r. Remember when I talked about it before? And then I just put in what I originally had, and I just put 4 pi r out because they're going to be constants. And I just had square root of r squared minus y squared. Now this is a very long process, and I'm going to show you what I did quickly on it, but I'm going to do that in the end. But I'm going to show you how I integrated this, but I'm going to show it to you at the end. So originally we had 4 pi r, which is this. Now what I get from the integral is r squared pi over 2. Then when I simplify it, it's just pi squared times 2 times capitalized R and r squared. And this is actually, if you search and Google it, this is what the volume of the torus is. So it's actually very interesting. It's a quite simple process in the way you look at it like this, but the things that take a lot of time is the integrals like this. So now that we've already gone through that step, I have my work on here. And I'm going to be zooming in and showing you, but this is a very quick process. I skipped a few steps in here because there's some steps that it just seems a little bit too much itty-gritty details that you should know. but you just start here with the 4 pi r. This is what I have. Now, what I did in here is I did u substitution for trig. So for my little r, it's going to equal. It's going to equal to y secant u, and that means that dr du is equal to y secant u tangent u. Now, based off of this information, this is how I'm going to continue on through all my steps. So if you ever wonder where she got those values, it's always based off, technically it's based off of my triangle, and what is my cosine, what is my sine, what is my tangent, what is my secant. In this case, I just use tangent and secant, but those are the most important things that you have to remember. So that's what I plug in here, okay? And when I do that, now I still have to solve this integral, so I simplify it, okay? You can also use a trig identity, tan squared plus 1 equals secant squared. And I forgot to put it down there, but that's another trig identity that must be used here. And so I get secant cubed minus secant, and now I'm going to separate those two integrals for you to solve. And you see here, that's what I do. I just separate them, and I also put the constants separate because they both have to get them. And I continue to solve secant cubed u, and I actually had to do another trig identity here, but I skipped that step. And also you need to find the derivative of secant u. And in this case, it's just secant u tangent u over 2. And so this is what you solved. And don't forget, you still have to have that constant there. And the next step that you have to do after you find out what the integral of this is, you have to plug in what you substituted, which for you, which in this case is y secant. If it's secant u, then it's r over y. So it's a little bit of a long process to plug it back in, but you must do that in order to solve for this. So I plugged them all back in. It was a little bit tedious, but I got it. And after you do that, I put down the bounds here. I accidentally put plus c, but actually it's not plus c because we do know what bounds we want. It's negative r and r from what I showed you before. And when we do that, that's how I got the value, and I showed you the simplified version of this, which this is the volume of the torus, or the donut, if that's what you want to call it. So those were my steps to solving it, and I hope this was helpful, and that is how you solve for it, and yes, alright, thank you.